Everyone, I'm very pleased today we have the opportunity to have Professor Shigui back to the Fields Institute after many years of involvement with many activities of the Fields Institute. Professor Shigui has a very strong academic root in Canada. He received his PhD degree from University of Alberta, and then started as junior research fellow at the Fields Institute when the institute was inaugurated and with physics side at that time in Waterloo. And he became a faculty at University of Harvey. There he also was awarded Killing Award. And then he moved down to University of Miami, to great north of Canadian mathematics. But Professor Yuan kept coming back to Fields Institute for coordinating a variety of activities, editing some of the special issues with the Fields Institute, and think the next Fields activity he is going to co-organize is the workshop in the summer. And Professor Yuan is now a professor at University of Miami, where there he also was awarded Cooper Fellow by the faculty of University of Miami, and he is on the editor board of many important mathematical biology and especially infectious disease modeling journals, including the BMC infectious diseases. And today I'm very glad that he is here and to share his progress in the modeling the influence of human behaviors and social factors. So Professor Shigui.
Yeah, Jianhong, thank you so much for the introduction. It's really an honor for me to come back to Fields because I started my career there. Well, I was one of the, as I mentioned, one of the first set of postdocs there. I mean, it's just unbelievable. It's been 30 years. It's kind of feel old, you know. So today I'm gonna mention something, you know, to me even it's new, which is the influence of human behavior and social factors on the spread of infectious diseases. I'm gonna present more result from other people, introduce some concept and ideas instead of reporting what I've been doing, okay? Before doing that, let me quote what Newton once said. I can calculate the movement of the stars, but not the madness of men, okay? After the famous South Sea bubble, okay? So from infectious disease, you can see this is the madness of men, or I mean, the social behavior of humans is complicated. So basically, especially after the COVID-19, there's thousands of papers modeling the COVID and other infectious diseases. And simply put it this way, you just try to give an example. So what do we usually do? You classify the population into 4 different categories: the susceptible group, the infectious group, the recovered group, and also when you have vaccine, you have vaccinated groups. And most of the time, we just write down 4 equations for each group and using certain functions describe the transfer from one group to another group. For example, the beta here, intentionally I write it as a function of T, S, and I. This is the transmission rate between the infectious and the susceptible individuals. And gamma is a recovery rate, and phi is the vaccination rate, and psi is the waning rate. So when most of the time when we write models, we just simply take, let's say for them, beta is just beta as a constant times S times I is the so-called mass action, and gamma is just proportionally the infectious will recover. And same thing for the vaccinated group is some certain percentage of people is going to be vaccinated. We wrote this kind of form automatically, you know. What is enough to describe the vaccine, the recovery, and so on when we consider the social factors, the human behavior. To start with, let's consider vaccine. I mean, here now, when we expect, when talking about, everybody knows vaccine because of the COVID-19, right? And this is certainly, this is it depends on human behavior. So the decision whether to vaccine or not is completely personal decision. It's not mandatory. Some of them mandatory, right? And most countries, in fact, apply a voluntary compliance when vaccine is talking about, right? And not because vaccine has side effects, right? And if the vaccine does not protect you, even hurt you more, of course, that's not a good idea to take the vaccine, which makes sense. Also, there's another idea is called free ride, because if the majority, because of the religious reason or other belief, or due to the lack of awareness, and if a majority of people are vaccinated, the rest, if which is small fraction, can take a free ride, right? So, on the other hand, if individual decisions, individuals decide whether or not to vaccine according to self-interest, then the herd immunity may completely different from what is best for the whole population compared to the mandatory vaccine. So when we're talking about vaccine, especially talking about the humans' attitude, US general public's attitude toward the vaccine, we needed to mention the famous research fraud on the measles, mumps, and rubella vaccine and autism. And this is a very famous story, in fact. What happened is in 1998, a doctor whose name is Andrew Wakefield, okay, a former UK physician, and his group published a paper in the Lancet. In the paper, they show that they study a new syndrome called autism enterocolitis, and raised the possibility link between autism and the MMR vaccine. So they claim that the parents have 8, so they have a sample of 12 kids. They claim that 8 of the 12 had symptoms, which is they describe the behavior symptoms with MMR, and report that the onset of these symptoms began with 2 weeks of the MMR vaccine. So they link 8 of them are related to the vaccine. So this is a huge story, and then this fueled the vaccine scam, and then consequently the anti-vaccine movement worldwide. Well, there was some people against the vaccine, but this just, put a fire on that movement. The claim in the paper were wide report, leading to a sharp drop in vaccine rate in the UK and worldwide. Okay, and because for them, this is measles, and there was a whole generation was not well vaccinated. So the 2019 vaccine outbreak worldwide was a consequence of this fraud, and this is the data shows you. Okay, because 2019 is about 20 years later. You can see this huge increase of number of infections worldwide in more than 40 countries. So in fact, this is fraud because later on, people try to question him, try to find out what's going on. So the investigator found that the doctor had multiple undeclared conflicts of interest, had manipulated the evidence and data, had broken other ethical codes. So consequently, in 2010, Lancet retracted the paper. At the same year, the UK General Medical Council suspended his license. He cannot practice in UK anymore. But the damage is there already because 2010 is more than 12 years after the paper. So, however, the damage was down. So, worldwide anti-vaccine movement already started and continues to now. So, and in this event, the whole thing was characterized as perhaps the most damaging medical hoax of the last 100 years. And then even now, if you go to Facebook and Google and Amazon, you can see tons of anti-vaccine argument books by famous people, celebrities, and politicians, even our former leaders and so on, right? And this movement is still keep going, and even toward the COVID vaccine, because this data was reported by the NPR and PBS network. The pool shows opinions about more than 1,000 United States adults. The question was that if a vaccine for the COVID virus is available to you, will you choose to be vaccinated or not? So at the beginning, you see, this is at the end of 2020, around 60% people said yes, okay? And around 10% says no, I'm not sure. But more than 30 says no, I will not take it. So of course, this data changed. Those who say yes, all vaccinated. Those who say not sure, some change ideas because they became vaccinated. But those who say were not, well, I mean, around about 10% change, but there's still closer to 20% who says no, okay? So even less, I don't know what happened in Canada, but at least in Florida, there's a lot of stories in the summer, in the last year, in the summer, because there's many people didn't take the vaccine and got infected and passed away. There were news about that. For example, in August, one story shows that there's a guy who is 28 years old. He got the vaccine and he passed away. And the church decided to hold a vaccine campaign at his funeral. Okay, of course, you know, an agreement with his family. But this report didn't say how many people were vaccinated. In fact, there's another story, and also in August, this guy in fact is a deputy. So he was 32 years old and he had 5 kids, which is tough, right? And he didn't vaccinate, and then he got infected and passed away. So the police department, also church, organized a activities, vaccine activity, and they reported that 94 people, in fact, vaccinated, in those days, organized by the family in the church. So you can see this is a sad story, but this sad story contributes positively because influence other people to do that. So this also shows you the psychological factors is there, because when when those people see their friends or relatives died from COVID without vaccine, they rethought about that and maybe take different actions. So this figure just show you. I just downloaded from this morning from the website. So this is the COVID data, even for Miami-Dade, and this is you can see how many outbreaks. 1, 2, 3, 4. This is the 4th one. This is the hardest one. So the solid means the cases. The bars indicating the vaccination. You can see the vaccination population is increasing. This Miami-Dade probably has the highest vaccine rate now, and in the whole Florida, there's more than 5.75 million people infected. Even in Miami, we have 1.16 million people infected. The population is 2.77. So it's almost 40% of people get infected. Okay, so this is a big deal. Okay, so now talking about vaccine, when we do modeling, what we need to consider, there's one method is taking the theory game into consideration. So there's a concept that is called the Nash Equilibrium, right? And so in game theory, the Nash Equilibrium is the most common ways to define the solution for a non-cooperative games involving 2 or more players. So if each player is assumed to know the equilibrium strategy of the other players, and if somebody want to change, nobody will gain. Then that strategy is called at equilibrium, Nash equilibrium. Okay. A famous example is the so-called prisoner's dilemma. So you have 2 prisoners, A and B. They got caught. They are suspected to commit a robbery together, but they are isolated and they are argued to confess. Now each is concerned only about getting the shortest possible, sentence for himself, and each must decide whether to confess. or without knowing the other's decision. And however, they both know that first, if both confess, then both go to the jail for 5 years. If neither confess, both go to the jail for 1 year. And third way is if one confesses, another does not, then the confessor get free and the silent goes to the jail for 20 years. So the best solution is do not cooperate. Think about themselves. So if they both confess and go to the jail for 5 years, this is the best. Okay. So in other words, this is a Nash equilibrium. Is selfishly, uncooperatively is the best for their both interests. Okay. So taking the game theory, putting the game theory into epidemic model was a hot topic. And one of the early papers by the Canadians, the Chris Bouch and David Earn, they published a paper in the PNS in 2004. So the vaccine game has each member of the population of N individuals play a strategy. So the vaccine with the probability P. Okay, so that's the strategy. So this is of course there's two risks. Here's the risky from the infection, from the disease. Another risky is from the vaccine. If the ratio of the two risks is R, which is presumably is a constant. So this is, I'm going to come back to this ratio later on. Now let's use P sub pi to represent the risk of infection if a fraction of P individual is vaccinated. So then the expected payoff of the individual playing strategy P is, the negative R, the ratio times P minus P pi times 1 minus P. So that's the expected payoff. Now suppose you have a P strategy P, which is at a Nash equilibrium. If no players can improve their payoff by switching to a different strategy Q. Okay. So then in this case, suppose a fraction epsilon of the population vaccinates with probability P, and the remaining with probability Q. So the overall the vaccine coverage, of course, is the epsilon times P plus epsilon 1 minus epsilon times the remaining Q, right? So then you can know then the payoff, of course, is pi of this P minus your R, and of course minus the difference of the two strategies. So this is the expected payoff. Okay. Now if you switch, okay, then you switch. Of course, this delta E gives you a measure for the incentive for you from changing from Q to P, or vice versa. So therefore, giving any risk R, there is always a unique strategy P, such that the payoff is strictly positive for all strategy, which is different from P, and for any proportion of epsilons. Okay, when epsilon is between 0 and 1. So this is the concept. This is the basic notations. Now, in the paper, they consider a standard SIR model. So you can see the equations here. And the only thing is here, P. P is the vaccine rate, or vaccine update rate. So of course, beta is the transmission rate, and 1 or gamma is the infection period. So we know that the basic reproductive number can be found explicitly, which is beta over gamma plus mu. And if we know the basic reproductive number, then the critical coverage of vaccine can be determined, which is P critical, that's a certain ratio of certain percentage of individual we need to vaccine in order to eliminate the disease. Of course, that depends on R naught. If R naught is less than 1, then this is 0. If R is greater than 1, this is 1 minus 1 over R naught. So that's what we use to estimate how many people we needed to vaccine for COVID. Right? So therefore, then the probability of, if somebody is not vaccinated, then the probability of infection is pi of sub P. That can be given in terms of the R naught and the probability P, which is 1 minus 1 over R naught minus P. So therefore, we can find the Nash equilibrium. Okay, for this case, remember pi sub P is the probability of infection with a certain population P infected. If P equals 0 And especially if the ratio, that means the ratio of get sick virus, you get sick because of vaccine. If the R is greater than that one, of course, then of course the 0 is the Nash equilibrium, right? We don't need to worry about that. And on the other hand, if R is less than pi naught, then you can find the equilibrium, the Nash equilibrium, which is 1 minus 1 over R naught times 1 minus R. So the R plays a very important role. Remember, R is the ratio again. So this is the unique equilibrium. Now, if R is greater than 0, so that means it's impossible to eradicate disease if you use voluntary policies, okay? On the other hand, if R is greater than 1, that means the vaccine is more harmful than the disease itself, then nobody, of course, would take it. So finally, if R is less than 1, okay? Remember, I think when Chris Bouch and David Earn was studying the problem, they had the UK fraud in mind. So they were trying to see how that vaccine scale affected the measles program. So their conclusion is that when R is less than 1 after vaccine scale, even if perceived vaccine risk is greatly reduced, it will be relatively difficult to restore the pre-scale vaccine coverage levels. That's exactly happened because before that movement, vaccine for measles was like 90 something. Now is 80 something. It's 20 years later, still not back to that level. So in other words, what I'm trying to say is that when we try to model, try to consider vaccine, maybe we just cannot just say, well, I just a vaccine rate times a population as, maybe a little more involved. In fact, in the follow-up papers, Chris Bouch and then another paper, they shows that they use a step function to describe the vaccine rate. Okay, and also in fact, there's quite a few other papers talking about taking the game, the vaccine game into consideration. Especially this is a survey paper like here, this one. It's a very long paper, more than 100 pages. Try to study the vaccine by using statistical physics method. Also, recently I went to talk, Wendy Wang from China. They proposed a model to study the vaccine games in COVID. So he used a function like a linear combination of things. Okay, so you have to consider different factors. So in other words, maybe the vaccine rate is not a simple constant times the S population. Okay, so that's the first part I'm going to mention. Okay, so the second part is the social inequality in infectious disease. Social inequality results from society organized by hierarchies of class, race, gender, and many other factors. Okay, that in fact unequally distributes access to resources rights. Okay, so social inequality is characterized by existence of unequal opportunities and reward for different social positions or status within a group or society. So it contains structured and recurrent patterns of unequal distribution of good, wealth, and opportunity, reward, and punishment, and so on. So of course, then for as infectious disease is talking about, this is also distributed unevenly through the society, in which the vulnerable, the poor people bears a disproportional burden. There are many studies showing that. For example, some years back, there were studies showing, in fact, as everyone knows, about malaria. So in Africa, some poor families were not able to afford, the band net, which is treated with an insecticide. And also, when those families were poor, because when they got infected, they were not able to looking for treatment on time. Okay, so in fact, those infected are gonna stay in that status longer, which cause more infections. And because they are poor, they got infected, and which make them poor. So this is very typical cycle. Okay, and also some years back, I was studying the hepatitis C in China. I was puzzled by the data. So the geographical distribution of HB cases in China was kind of strange. So along the coast east side of the country, including Shanghai, Beijing, and also Guangdong and so on, the cases is lower, but in the middle part is higher. In the west, it's much higher. Later on, we found out, in fact, in 1992, in fact, the HB vaccine was discovered, was tested in China, and China was the first country to use the vaccine. But in 1992, the Minister of Health recommended the virus to the general public, but was not free. It would cost 159 yuan renminbis at that time, which is a big amount of money. So any of those rich family in the east part or some in the middle part were able to afford that. So that caused this problem. Okay, so this is again this is socioeconomic inequality, okay? Because the poor family will not afford to vaccine their kids, and later on the kids got infected. So some years later, the government probably realized that. So in 2009, 2011, the government retroactively immunized more than 60 million young kids, younger 15 years. But the problem was there, right? It caused a problem. This is again social inequality. So 5 years ago, there was a survey paper published in the Norwegian Medical Journal, and the survey was about the two influenza pandemics in 2018, 2009, and which shows that the EU countries, including United States and Canada, Australia, and in those countries, the poorest people suffer the highest risks of infections, having a severe disease. Okay, in both cases. Okay, now also even for this COVID-19. There were papers published in the New England Journal of Medicine, also in Nature. The poor people, certain immigrants groups, Black people, and certain Native people, once again, are paying the highest cost for the current pandemic. So this is so obvious here. So again, going back to the figure I showed you, the diagram here. So in other words, now you're talking about the infectious, usually we take it for granted, the constant gamma times I as the recovery rate. But according to what we said, that the poor family will not afford that. In fact, that's not a constant. Maybe that depends on many other factors, social inequality, social economy studies. But how to do that? Honestly, I don't know, but this is certainly something we needed to look at. Maybe I can show you one of the examples I did before. So a few years back, we had an NIH grant working on vector-borne diseases in the Middle East. So we studied the Reef Valley fever in Egypt and some other countries. So we did consider these seasonal change and socioeconomic studies. So what happened is here. So we have a virus which is called Reef Valley fever, which is among animals, basically, including cattle, sheep, and camel, and goats, and so on. Human can infect, but usually is through handling the animals. So because the virus was originally found in Reef Valley in Kenya in 1931, so this is named the Reef Valley fever. Okay, the outbreaks of the virus reported in sub-Saharan in Africa, Egypt, Saudi Arabia, and Yemen. Okay, so this is the virus looks like. Okay, so the 5 major outbreaks coincide with either the peak season of the mosquitoes or the timing of the Great Barren. Okay, or it's called the Feast of Sacrifice. So this Adil Adha, this is the largest Islam festival at which time very large number of livestock are driven towards the side of the fest. Okay. So in Egypt, Arabia, and Yemen, outbreaks may occur when the disease is introduced by importation and transportation of those animals. So it was reported that usually more than 1 million of sheep, more than 750,000 from Somalia and 350,000 from Sudan were imported by a company, okay, for this project. So, and this, okay, let me try to finish. So this festival falls on the 10th day of the 12th month of the Islam lunar calendar. So it creates a particular periodicity of times of high potential for the outbreaks, because the river flood stage follows the solar, I mean the calendar, which is 355 days, while the religious feast festival, this is lunar calendar, is 354.737 days. So these two events will coincide perfectly every other 33.57 years. So in order to arrive at the rendezvous, that is the Nile Delta, well, millions of the Muslims celebrate the festival by ritual sacrifice of ram by Aha after long distance travel. People travel by food, by train, and so on. Okay, so what are they? I'm going to show the map. They start from Sudan and follow the Nile River, and then from the south to the north, and then travel to the southeast part of Saudi Arabia, where and along the Red Sea. Okay. So this event, in fact, is why it's socio-economic. Okay, here, this is the map. Okay, so this is from Sudan along the Nile River, and to Egypt, and then to Saudi Arabia. And this event is socio-economic because every family makes contributions, and the contribution depends on your status, economic status. If you're rich, you have a big family, of course you contribute more. For example, you contribute a camera or big animals. If you are relatively rich, you may contribute proportionally small. And if you are not that rich, then you can contribute a sheep, a goat. If you are poor, you don't, then you contribute the labors. Okay, so this is a completely socioeconomic activities. Okay, so at that time it was supported by NIH, and then in one of the early papers published by one of my former students, Dao Gao, published in Bulletin Mathematical Biology. So we use a patch model. We use 3 patches to describe the 3 locations, so that you have movements from each patch, and we study how those movements contributed to the outbreak of the problem. So in the paper published in the PLOS in the laboratory disease, we generalize the model by considering the periodicity. So you have the annual change of the rivers and the seasons. Also, you have the annual movement of those people doing this kind of gathering. So you can see the coefficients are periodical. Okay, so the directions in the dash represents the seasonal or sociodynamic driving flows. Okay, driving flows here, driving flows here. Okay. All right, now, so we did lots of simulations, and this is the simulation of the model, and we have pair solutions. Especially, we could have resonance cases because you have 2 periodical going on. As I mentioned, every 33 years, the 2 coincide. Also, we studied if you start the daily increasement of the movement. So if you move faster, how that's gonna affect the disease outbreak. And if let's take a long time to prepare. If you start earlier or you start later, and how that is gonna affect the outbreaks and so on. We did lots of simulations. But in summary, in this study, we proposed almost periodical 3-patch model to investigate the transmissible dynamics of the Rift Valley fever among the ruminants with spatial movement. So this simulation shows that in the northeast of Africa, the human activity, including the social, the festival, along with the combination of climate change, such as rainfall, socioeconomic factors, and hydrological They will all contribute to the transmission and dispersal of the disease. Okay. So sporadical outbreak occur when the two events occur together. First, you have a lot of animals moving on. Secondly, you happen to have the season where then they have a large number of mosquitoes. Then definitely they're going to have outbreaks. Okay, so this is showing one example. So the last part I'm going to mention the influence of the psychological factor. So in the later 70s, the Italian mathematician Capozza and his co-author published a paper in Mathematical Bioscience. So they studied the cholera epidemic in Paris in 1973. And they introduced a saturated incidence rate. So it's not single beta times I times S. In fact, it's GFI times S to model the so-called crowd factor and protection measures. Moreover, they introduced a phenomenon which is called the psychological factors. Okay, what are that psychological factors mean? So now we experience that when we're talking about COVID-19. So if the newspaper and TV and social media report very large or increased number of infected individuals, then those people who are not infected will be cautious, will take actual measures to protect yourself. So because you take some measures, of course, the interaction between the infected and susceptible is going to be reduced because now a large number of susceptible individuals will take protections. So in other words, when the number of infectives increase, the infection, in fact, decreases. So in their paper, they even give this figure to describe the so-called psychological factor, because the psychological factor, the infection rate, in fact, decreases when the number of infectives increase past certain numbers. So they gave this figure here, but in the paper, they did not give any specific function to describe such incidents. So a few years back, me and my classes try to see whether or not we were able to find a function to describe this kind of curve, the so-called psychological factor. In other words, the question was how to characterize the psychological factor using a specific function. What is the impact, the psychological impact on the dynamics of the model? So we can go back to the one of the early papers by 711 Iwasa and 711 student Weimin Liu. So in their paper, they propose a very general incident function. So k times I to the power L times S divided by 1 plus alpha I to the H. The denominator, 1 over 1 plus alpha times I describe the psychological factor, okay? So of course, the L and H are important, okay? Now if H equals 0 and L equals 1, that's the standard in the mass action, right? We know that. Now, so also because there are two integers here, two powers, L and H. When L is greater than H, of course, then the function just like the standard bilinear function. The function is unbounded, right? Increase. And there's a case where when the two equal, when L equals 2 equals H, then you have saturation, okay? This is just like the mechanism momentum function. However, there's a case when the power in the denominator H is greater than L, for example, when L equals 1, H equals 2, then you can see the function goes up and reach a maximum and then decrease. So this is similar to the figure Capozza proposed. Maybe we can use this one. So that's what we did in 2007. My collaborator, Dongmei Xiao, and then I published a paper in the Mathematical Science. So we use this function. So the numerator here, I is, the power is 1. In the denominator is 2. As I mentioned, Ki measures the infection force of a disease. And then the ratio here, this measures the psychological factor from the behavior change of the several individuals when the number increases. So if you put this one into the standard SIR model, where you can find the basic reproductive number. It turned out the dynamics is pretty standard or pretty trivial in the sense that when the basic reproductive number is less than 1, the disease-free equilibrium is globally stable. Otherwise, when R naught is greater than 1, then you have an endemic equilibrium, which is also globally stable. So this is, from the math point of view, this is clear. This is trivial, okay? But that doesn't tell you too much about the impact of the psychological factor. But if we look at carefully, okay, we did some simulation. So say, suppose this is the number of infectives, okay? And as I mentioned that the alpha, okay, the alpha affects the psychological factor. When alpha take different values, you can see the number of infectives drop dramatically, right? If alpha is larger, you could have like 150 people infected, and then 100 people infected, and then less than 50 people infected. So the psychological factor does affect the dynamics in the sense affect the number of infectives. The behavior, the long-term behavior does maybe not so obvious, but it does. It does. Okay. So this is one of the cases. So in fact, later on, we found that maybe mathematically we can do a little bit more. Say, for example, we keep a function like that, okay, a more generalized, non-monotone and saturated incidence function, like you have quadratic terms in the numerator, quadratic terms in the denominator. But then you have a parameter beta, which does not have any biological meanings. It just changes the shape. When beta take different values, say beta equals 1, the function is increasing. When beta equals 0 or beta equals negative 0.5, then you can see that you have the saturation factor. But when beta becomes negative, but is greater than negative 2 over square root of alpha, then again it's increasing and decreasing. So if we replace that, the previous one by this one, then the dynamics is no longer trivial. It's going to be much, much more complicated. You can have a lot of interesting dynamics. For example, you're going to have a weak Fox multiple of 2, and you have a cusp of codimension 2, and you could have all kinds of application, including set-knot application, Bagnetov-Taken application of codimension 2, hop application, and even degenerate hop applications. Okay, and even we. So, by the way, this paper is by colleagues from Central China Normal University, and also Pei Yu from Western. Okay, and we show that in fact, in some cases we have 2 limit cycles, which is showing more complicated dynamics. And in another paper we just published, if the numerator is this linear, then the model could have 3 limit cycles. So the dynamic is no longer trivial if the function takes a little bit more complicated ways. Okay, and also we use this model to simulate the data, the influenza data from mainland China, the data from 2004 to 2017. So the dashed data, okay, is red, and the solution is from the model. Okay, so that's the simulation. We kind of simulated the data, so the model does make some sense. Okay, so in summary, what I have tried to do is to try to show you that human behavior and social factors play very important roles in the spread of infectious diseases. Understand the influence of them on the spread of disease can be a key to improve the control efforts. I think everybody's convinced that because of the COVID-19, this is just daily lectures for everybody, right? Of course, if you believe in vaccine, and so I recently some recent studies on the influence of human behavior and social factors with rare diseases, and also studies or data on vaccine decision using Nash Equilibrium strategy to impact the social inequalities and influence of social factors were reviewed. So I presented some results, also present more problems, because there's some points are very important, but even, I mentioned, I don't know how to model them properly, but in the next project, and maybe when we try to model some infectious diseases, maybe we needed to consider them, So that's what I want to talk about. Thank you very much.
Thank you, Shigui. And this is very nice, also indicating a change